Modern deep learning models are built on rigid, uniform grids of artificial neurons. But when you closely examine actual biological intelligence, that dense structure completely collapses into an irregular, asymmetrical web. Recently, the Flywire Consortium achieved a massive milestone. They completely mapped the adult Drosophila melanogaster, or fruit fly, connectome. A connectome is a comprehensive physical wiring diagram of a brain, and in this case, it captured exactly 140,000 neurons connected by 50 million individual synapses. This map functions as a naturally evolved computational blueprint, refined over millions of years, to coordinate movement and process sensory data in three-dimensional space. However, attempting to execute this specific biological blueprint exposes a severe structural flaw in the hardware we rely on to run modern artificial intelligence. Artificial neural networks, or ANNs, and the graphics processing units, GPUs, that power them are engineered to perform dense linear algebra. They require homogeneous, evenly distributed matrices of data to operate efficiently. Biological networks, however, operate with wild irregularity. To simulate and utilize brain-scale intelligence, brute forcing this data through standard GPUs results in massive inefficiencies. We have to adapt to the geometry of the biological graph at both the hardware and algorithmic levels. This chart displays the connection distribution for fruit fly neurons. Notice the extreme upward curve at the right edge. While most neurons connect to a few dozen neighbors, a tiny subset acts as massive data hubs, with extreme fan-in and fan-out counts exceeding 10,000 connections. This specific mathematical structure is known as a power law degree distribution. Because it is highly sparse and asymmetrical, it severely penalizes GPUs. When a GPU encounters this much irregularity, its cores are forced to sit idle waiting for memory retrieval, destroying its computational efficiency. To simulate the full 140,000 neuron model without fighting this irregular geometry, researchers turned to specialized hardware. This is Intel's Loihi 2 neuromorphic platform. Neuromorphic chips use a completely different physical architecture. Instead of separating the processor and the memory, a standard setup known as the von Neumann architecture, Loihi 2 co-locates memory and processing directly together on distributed neurocores. By keeping the memory strictly local, these neurocores communicate through asynchronous, event-based spiking. This lightweight protocol only sends signals when a neuron firing, easily absorbing the extreme fan-out of biological hubs without creating a data bottleneck. Neuromorphic hardware is a physical prerequisite for executing irregular biological geometry with true computational efficiency. Proving that the biological graph can be simulated efficiently is only the first step. The next challenge is determining whether this anatomical map is actually useful for controlling an artificial agent interacting with a physical environment. To test this, researchers developed the Fly Connectomic Graph Model, or FlyGM. Their objective was to use the exact static wiring of the fruit fly brain to control a biomechanical fly inside a high-fidelity physics simulator. This block diagram outlines FlyGM's strict routing. Starting from the Mujoko fly body, physical observations are projected into the blue afferent neurons. Signals then propagate through the green intrinsic neurons via verified biological synapses before the orange afferent neurons output physical torque back to the fly. Crucially, the researchers allowed zero artificial architectural search or structural tuning during this process. The topology of the network is completely locked to the biological wiring diagram of the insect. The FlyGM model tests the hypothesis that static biological anatomical maps can be directly compiled into functional, dynamic policies without relying on human-engineered corrections. This raises a question. Does rigid adherence to biological wiring actually yield better robotics control, or is it merely an aesthetic choice? To find out, the FlyGM model was tested against 3 rigorous baselines: a standard multi-layer perceptron, an Erdos-Rainey random graph, and a degree-preserving rewired graph that maintained the same number of connections but scrambled their targets. These graphs show the results of the imitation learning phase, measuring training loss and action error. The exact biological connectome drastically outperforms the artificial structures. The red FlyGM line converges much faster and achieves significantly lower error than the baseline traces. This bar chart compares the angular error across the models during a highly complex maneuver. a high-yaw turning task. While the FlyGM model maintains an error of just 8.29 radians per second, the random graph experiences catastrophic angle drift, towering at 125.36. This sequence of simulation frames shows what that successful biological execution actually looks like in the engine. The biologically wired agent easily executes the high-speed left turn while maintaining complete stability. By analyzing the mechanics of the turn, we see the agent naturally modulating asymmetric stride lengths. It reduces the stance amplitude on its inner legs to pivot cleanly, a behavior it executed without being explicitly programmed to do so. The FlyGM architecture also generalizes beyond terrestrial walking. It successfully manages the entirely separate physics of stable aerodynamic flight, keeping its body orientation perfectly aligned with the target direction. Managing both walking and flying proves that the connect tone isn't simply memorizing a single stereotyped gait. It is encoding a highly flexible control strategy capable of adapting to entirely distinct locomotor demands. The biological graph provides a massive structural inductive bias. The physical wiring itself mathematically encodes millions of years of evolutionary optimization for physical locomotion in three-dimensional space. If we shift our focus away from the external physical performance of the fly, we can look inside the network's latent space to observe the internal computational dynamics occurring during movement. This graphic tracks the connectome's temporal dynamics during continuous locomotion. Within the heat map, distinct activation patterns fire across neuron superclasses. As the timeline crosses boundaries, from walking to pausing to turning, the clusters of functional segregation clearly shift in response. This distinct functional clustering and phase shifting occurs completely naturally. It is a sole consequence of the graph's structural constraints determining the flow of information, rather than any programmed behavioral rules. This highlights the convergence of two major breakthroughs. Specialized hardware like Lohi 2 has solved the physical bottleneck of simulating biological sparsity, while specialized algorithms like FlyGM have proven the computational superiority of biological topology. Together, they demonstrate the direct transformation of anatomy into intelligence. Static wiring diagrams act as dynamic control policies waiting for activation. By embracing the algorithmic irregularity of biology, we can bypass the brute force energy scaling of standard deep learning and instantiate true embodied intelligence.